Hello again. It's been a while since the last update, and yeah, primarily because I was on vacation and I didn't bring my laptop. Um, so anyway, I will talk about in this update what I have done since the last time. Primarily 5 different things. As you can see here, this was probably the most difficult one, just because I've never done it before. Not really. That's not true. I have done it before, but not in assembly. I will just go through them one by one. So the first point is reading from a file. So instead of, you probably remember the previous times, I've had a buffer here, right here, with my source code. However, now I have transitioned into actually reading from a file. So that's the file here, in.a. I don't remember why I called it A, but maybe because it's assembly compiler. I don't know, maybe. Anyway, so this is the file over here to the left. And it basically reads the entire thing, or currently it only reads 4096 bytes. Yeah, so I need to figure out how to actually find out how large the file is, but for now it doesn't really matter. So as you can see, I can now actually write proper code without just having to write on a single line. So yeah, that's good. And you can see here I have an enough parse, and just because of how my parser works, it's expecting one of these tokens over here to the right, one of these tokens, EOP tokens. So I just have to write it for now. That also means that I can use anything below it as like sort of like just plain text. It won't really touch it. It will just stop here when it reads this token. Yeah, and I can just talk about if you don't have a main function, this compiler, it will compile, but it will not be able to run because it needs this function. And currently I'm just testing running another function, so I just implemented a function call. I haven't done that before, so yeah, that's nice. Yeah, and how do I read the file? It's actually very simple. I can open up the Lexer. I have it here, read file contents. So I will fill this buffer address up. I will not fill it up. I will just, this is the pointer to where the address of the file contents is stored. So basically, first we open the file. So if you put 2 into rags, it's the syscall for open, and then you just give the file name. And I have an external file name, and it's because it's defined over here in the config file. Then you just push the pointer into RDI, and you only want to read. And I don't actually remember what this is. This is the protection, maybe. I don't remember. Whatever. It sets RDX to 0, and then syscall. Then we get the file descriptor in regs. Then we can move it into the next syscall, which is mmap. I had some difficulties actually getting mmap to work, and then suddenly it just worked. I have no idea why. It's just, I don't know. Sometimes assembly is just fun. So anyways, it needs to go into R8, which is the file descriptor. What do you want to memory map? That's what mmap means, memory map. So you map the files content into memory. Yeah, you give it a bunch of parameters. This is basically the address. If you wanted to place the allocated memory somewhere that you find nice, then you can give it an address. But if you just pass it in null or 0, then it will just choose some place for you. And then you will pass in the file size, and for now it's just 4096, 4000 bytes or 4 kilobytes. Yeah, that needs to change later on, but it doesn't really matter. And then the protection bits, I had a lot of difficulties finding out like what the actual correct flags for this was. But then I just booted up C and tested it. It's because these are like map private and prot read and stuff like that, and I don't have access to those pound define definitions, so I had to do some manual work. This also means that it's not really that portable. It will probably only work on my machine, or people who have a similar operating system as I do. Whatever. And then there's this offset. It doesn't really matter, just put it to 0. I don't remember actually what it does. Probably some offset into, I don't know, somewhere. No idea. But anyway, when you call syscall, you actually tell the operating system to please take everything that this file contains and then map it into this memory region. And then you get a pointer to the start of that memory region. And then I just store the pointer into my buffer racks. And then I don't have to do anything more. Some people will probably say, oh, you need to close the file, but no. I'm of that belief that the operating system needs to do that for you. It keeps track of your open files anyway, so there's not really a point in telling the operating system I'm done with it. Okay, there might be a point, but okay, your compiler is not going to take that long, so it's not really like it's hogging up the source file. And it's the same as the unmap. You don't really need to. If your program is not going to run for that long, you don't ever need to call free or unmap anything, because it's the operating system's job. It's going to do that anyway. So yeah, you're free to do whatever you want. So that's basically reading from the file. That's a very nice quality of life feature I added. Then I added structs. I can just show you how it's defined. So you have to type struct and then some identifier you want to call your struct. I have played with the idea of calling it point, and then you just do the brackets, and then you can do x and y. And I think, do they need to be like this? I think they're like this. I implemented them last week or something, so I don't. Oh yeah, it is like this. Yeah. So this is the syntax. And then if you want to make a point, you just type struct point, and then some point, so p. And then you can say p.x equals 42, p.y equals 1. And then you can print them. And then I have made a script which basically just calls clean, and it constructs everything again, and then it compiles it into a code.s file. It links, assembles it, and it links it, and then it executes it. So we can try and run it. 42 on 1. Nice, it works. So that's very nice. If we look at the source code that it constructs, this is kind of annoying, it's only on one side anyway. So you can see here, it makes room for 16 bytes, and because I'm using, my standard is that I use 64 bits for everything, so this means that this X gets 64 bits of memory, and this Y gets 64 bits of memory. It's basically like a long, so that's why it's 16, because 8 bytes is 16 bits. 64 bits. So 2 times 8 is 64. And then we do a push of 42, and we pop it into racks, and we store it into the X register. And I think maybe I have reversed the order, but it really doesn't matter what order you have them in. And then I push the 1 into the next spot, which is this one over here. And then we can print it. So we move it into racks, the X variable, push it, pop it, and print. And the same with the Y value. And that's basically it. So seamless, very neat. Now that you can see there's a lot of push and pop, but you can do something later on called peephole optimization, where you can modify this. So if you do this, let's just see if I can do this. If you have this code, you can change it into so it first recognizes that you do a push. You have a push plus a pop. This is the same as doing a move 42 into racks. So this means that you can replace these two instructions with this one instruction. So if we do that here, then we can do this. And now we only have this. Then there's another pattern where you can see, okay, I move 42 into racks, and then immediately after I use the racks register to move it, the value 42 into some other place. You can say, okay, this is also a pattern that I can match on. So I can do, this is the same as saying move 42 into the destination here. So these 3 operations can be computed or converted into this one instruction. So don't worry about the instruction size right now, because it's going to become better. Yep. So let's talk about how you might want to implement structs. So first off, you need to actually be able to parse it. If we look here, we can see this here determines the length of your struct, and I can just show you my data structure for structs. Let's see, struct buffer. Okay, this is the struct buffer. So we have a name descriptor, that's the point. Then we have a count. For this instance it's 2, and then we have some field descriptors. And this syntax here is just an array, so there can be variable many field descriptors here. So it's just a bunch of identifier descriptors, like I've been using all along, like kind of like this point descriptor. So it says place the point descriptor here in the first place, then place a 2 here, and then we place x followed by the y descriptor. Yeah, so that's how kind of like how you want to lay it out into memory, or how I did it at least. So that's the first problem. Then you get into a problem where you want to have some sort of access methods, or how do you access into your struct? Like you need some way to identify each struct instance. So I came up with the idea to make a struct instance, and you do that by writing struct point p. So this is the type, and this is the variable name. We can find a struct instance here somewhere. Okay, I haven't written it to memory because it's very simple. It's just a struct name and a variable name. So 2 descriptors. So the first part is the point, and then the second is this p. So point and p. So I have, remember, I have stored this point somewhere in memory, and now I can store this p somewhere in the memory. So I have this tuple. So I can look this struct up in my data structure later on. So yeah, that's how you do an instance, and then you need to do a field access, which is this part. Is this also just two descriptors? It's the variable name, so the p. This I call the struct name. It's not really correct. It's more variable name, but whatever. So p, and then the field descriptor is the x descriptor. And then you can just like look up, okay, I have a p, then I need to look up through my struct instances. Okay, what is a p? Okay, it's this point. It's the struct type is point, and then I look up the point, and I find, okay, it has two fields. One is x and one is y. And for this example, I want to assign 42 to p.x, the x field. So I just tell or look up in the symbol collector, okay, what is the offset for the first one? And in this example, it's 16. And then it just assigns 42 to offset 16. And then for this one, it's 8. Just like we saw in here. 16 and 8, right? Yep. So that's kind of like how structs are made. It actually gets very fast to implement stuff when you first have a good foundation for your stuff. Like I can just kind of show you here, parser, and if we go to the constructions, look here. This is just like how you construct a function call. And I do the same way for all my functions, all my data structures. I lay them out in the same way, and I can just like copy paste. So you can see here, construct a function call and construct a def reference. It's basically the same code I have just copied over. And I do it like this, so I can mark this and then select them all, and then just do function call. And now is a constructor for function call. So very easy. You just have to remember to do the correct offset here. Yeah, otherwise bad things will happen. You will get misaligned, basically. Yeah, so it gets very easy. Another thing, actually, also, I have added some error handling. So you can see here, emit parse error, missing right parenthesis. So let's see here, if we forget to put a left parenthesis here, my IDE will tell me that I need one, but let's imagine you're just using something stupid. Then you can say main, and then it says missing a left parenthesis token. Current ID is 24, so it's a an identifier, and the peak ID is 37, which is a dot. So that way you can kinda somewhat find where you messed up. I need to add some line information to make it easier for you to debug your program, but this is a start. I have not added the error messages everywhere. I can just show you how I did it. I have a file called errors, which is basically just a bunch of this kind. So for example, this is emit not implemented. It just moves a pointer to a buffer, which I can show you here. So this is the not implemented buffer. It says this feature is not yet implemented, and then I just move this into RDI, and then I call this function emit parse error, which just emits the message to the screen, like you saw here. So first this is the individual error message, and then this get pasted to or with everything. It probably shouldn't if you are already done parsing and it's a logical error. Yeah, but whatever. So that's that. Let me go back to my to-do. Arrays. Arrays are also a thing. So now I have two types. I have normal primitives, 64 bits, like this A here, for example. And then I have types of points, and I want to make arrays of both of them. So I want to make arrays of just integers, and I want to make arrays of points, for example. And the way you do that is you do, for integers, you just do this, and then you have to specify how many you want. So let's say I want 10. Let's say I want 10. And I want to fill them up. A index I. Let's just fill it up with, I don't know, I. And we can do it again, and then we can print it this time. Yeah, so hopefully this will print the numbers from 0 to 9. It didn't. Okay, nice. Let's see, expected a number. It's probably this one. No? 10, okay. It's a bracket. What? Oh, it's this one. Okay, right. This is actually not a mistake. It's just me being dumb. I must have it somewhere else. Nope. Number expected. Yeah. Okay, so this is actually not. Yeah, I need to do this because I thought it was something else that I did, but it's not, because this is actually valid. Let's try it again. Ooh. Oh, I forgot to do this. Okay, now we go. 0 through 9. Very nice. That's the result we expected. Perfect. I just forgot to increment the counter while I was looping through this, so everything is good now. Oh, we can also I don't think I have greater equal. I don't. This also doesn't work. Oh, I don't have negative numbers. No. Okay, let's just say while it's greater than 0. And then we can print this last one here. I haven't added support for unary on negative numbers like this. This is not allowed because currently I only support numbers like this, and you also want to support numbers like this, but I'm not doing that right now. A hacky way you could do it is just like pretend this is a binary operation, and then just insert the value 0 here. That's a hacky way you can get negative numbers, but it's just dumb. Okay, let's see if this works. It does. Okay, nice. Very nice, very nice. Perfect. Wait, why does this say 10? it's because I need to do this first. Okay. I have no out of bounds detection, so when I did this before, a index 10, what it did in actuality was currently I have the first 10 spots on the stack is reserved for this array, and then just above it is this variable here. So when I print a index 10, it's actually off by 1 here, so it's actually going to read this number here. So it just printed out the I instead. So that's why it did that. So if I do this now it should only print 9 to 0, and we even have the correct one. Perfect. Very nice, very nice. Okay, I'm getting off topic. I don't remember where I was. Let me just think. Oh yeah, arrays. So how would you implement this? Let's look at some data structures. Array assignment. So the first one, A10. If you know C, you know that you can put in C, it would look like this. Int A, square brackets, and then a number. You can do like I here, for example. You can do that because it needs to be a constant expression or a constant literal. So it needs to be a number. And the reason for that is you need to at compile time determine how much space you need to give this array. So if we look here, oh, I messed up. I'm not supposed to have this. I have a much simpler syntax. So here you can see, yeah, this is my guard. I'm a while loop, so I have 2 while loops and a guard. I don't think I have actually showed the while loop, have I? Probably not. Nice, fun, very fun. Okay, so you can see here I have 88, so that's 11. 11 times 8 is 88, and that corresponds with this number of, yeah, so I need to be able to determine how many offsets or how much I want to offset the stack pointer in order to fit everything I want. Yeah, so that you need to do it at compile time. You need to be able to determine it at compile time. So what is an array? An array is just an identifier, so you need some way to identify into it or offset into it. So that's the A, so that's the first part here. And then you need a count and you need a stride. And a stride is basically how long each of these elements are. So for just integers, it's just 64 bits or 8 bytes. But for a point here, for example, it's going to be 16 bytes because there are 2 fields for each array entry. Yeah, so it's the stride matters. Yeah, it matters how you access in or how you index into the array. That's the word for it. Nice. Yeah, so you need the identifier type. Because it can either be an identifier or it can be a struct instance, and then you need a count, and the count is this, and you can see it's just an integer, so that's very nice. So that's basically an array assignment. It's not really an assignment, it's just a declaration, because you just declare that I want 10 of these. Yeah. So that should probably get renamed. Yeah, and then you have an array access, and then there are 2 different kinds of array access. So there's like this kind of array access, and then there's this kind of array access. And you can see it's textual wise it's the same, but this is actually an assignment into an array offset or array index, and this is the value of indexing into an array. So there's a little bit of difference because you need you need to handle it 2 different ways. Yeah, so you want to know the identifier, so that's the array access, the identifier type and description, because again it can be an identifier or it can be a struct instance. And then you need to know the index type, because if you write a 1 here, you're actually able to determine the absolute offset at compile time. It just takes a base address of A, and then it adds the stride times this number in here. So for this, it's going to be the base offset of A plus 8. And if you do this, then it's just going to be this. And funny enough, you can actually do this. So because A is just an offset, it has a base offset, then this is completely valid. It's just always going to do this. A index 0 is going to be this value. So yeah. So yeah, that's basically that. And it's the same deal with these guys. You just do them here, points. Let's say I want 50. Oh, I played with a different kind of annotation. I actually kind of like this even more. I think later on I want to move the types to the right. So you do like this. Or maybe put them inside here. But then it's just a type of this, but then you don't know how long it is. So yeah, it should probably be on this side. And then for this you want to do int. I think this is what I'm going to do when I get deeper into this. Yeah, but not right now. So this declares that I want 50 of these. So it's going to allocate 100 spots because you have 50 x's and 50 y's. Yeah, and it's basically just the same. You have a base offset for your points, and then you have two different kinds of alignments, let's say that, because the x has, in this example, has -16, and the y has alignment 8, right? Or it should probably actually be 0 and 8 when I think about it. Oh, I don't know if... Let's just try. Ooh. Something is not working. Missing a token. I don't know why it's saying this. Current ID 10. That's this. So we are probably here, and the peak is 24. What? Oh, that's an identifier. Yeah, so that's this. Wait, we have this and this. It should have a dot here. Oh no, it's because we're here. Oh, we're here. This point and this. Okay, I don't remember how to do this. I need to look at that. But anyway, it should work. And it did work before. I just did some refactoring, and I can see that I made some mistakes while refactoring. Anyway, so that's basically how you want to do this. Then we have the pointers. So let's say I have a variable a, and its value is 42, the meaning of life. Let's print the value. Then we want to make a pointer to a. It's kind of like C syntax. We can print the pointer. Let's say we want to give we want to override what the the pointer points to. So we want to assign a new value. So let's give it the value 69, and then we can try and print a and print pointer. Oh, we need to dereference. (42, 42, 69, 69). Very nice. And this is the pointer. It's just a pointer on a stack. I had some troubles with. Originally I used this sign, but what happens if you do this? Then the compiler actually can get confused. It can either pass this, or it can pass this. Right, so you can see there's kind of like an ambiguity, and you can kind of argue that maybe it should be able to look ahead, but then I need to change how my parser works, and I don't want to do that. So I just changed the symbol. That's a much easier way to fix it, because this is just 2 times pointer. Yeah, but anyways, so that's why I did that. So it's actually kind of easy. You just wrap whatever's in here inside a deref, and up here inside a address of. You can see the the data structure for that. It's right here. So the address of, it's just an expression type and a descriptor, because it's always going to be an expression, and at this point it's always going to be a either an identifier or a struct instance. And then there's the deref. It's always going to be an it's just going to be an expression inside it, because this could be a function which returns another pointer. So like you can imagine like get pointer. This will return a pointer, then you dereference it, and then you assign the value of 69. That's why it needs to be an expression. Yeah, and that's just it basically. And I'm actually kind of proud of how simple it is. Let's go to statement, and let's find the, so like the assignment, you can just, here I just call the assignment. I want to construct an assignment, and I don't want to wrap the left hand side inside a dereference. But if I do a deref assignment, here, I do want to wrap, this is a 1, so it's true, and this is 0, so it's false. I do want to wrap the left hand side inside an assignment, or inside a dereference rather. So that's just a very easy way to reuse your functionality. So I just have, before I return, I do a dereference here. So I just load the left hand side, this, and then I construct a dereference, and then I just move it back into where it was stored, and then I can just continue as normal. So very easy and very nice. And the same goes for, if we go to parse expression, then we have here. This is just two different cases. So you can either return an address of or deref, and this is how I pass my, like how I adhere to the precedence rules. If you want to know more about it, I can maybe talk about it. It's not that difficult. It's just a bunch of grammar rules you have to follow. It's not that difficult, but you can see here are the different kind of tokens you can have. You can just have a number, an identifier, or you can have this kind of, this is an array index access, and this is a field access, and this is a field access which has an array index into it, and this is the address of, and this is a dereference. This should get changed to this. This is also where I will add function calls. So there will be a function call down here. Yep. Very nice, very nice. To do. So that's pointers and structs. I can maybe show how it looks. So let's see here. First 42, we want to store it into the first offset. Then we load it, called print. That's this. Then we want to load. We are here loading the effective address of this offset, so we get a pointer to this space on the stack, and we push it into racks, and then we store it into the next variable, which is this part. And then we print it, which is just the pointer. Then we want to assign 69 to it, so let's skip down here. So we just pop the 69 into rex, and then we load the pointer into RBX, and then we move rex into the values pointed to by the pointer. So this is kind of like the reference in assembly. Alright, so layer Q is the address of, and this is the dereference. So you have a pointer in RBX, and then you dereference using this. That's how that works. And then lastly, I can talk about function calls. I have only implemented with 0 arguments, and that's because you can see I need to implement the argument list. Like, let's say I have some variables here, so A, B, and C. Right? I need to somehow be able to pass this, and I need to figure out where to store this, maybe in registers, probably just on the stack because I'm a stack machine, or I'm developing a stack machine. So it's probably going to be super simple, but you never know. There might be some troubles. But basically right now it just finds, okay, we have an identifier, and we see there's an open parentheses. This means that because this is the start of a new statement, and then it's just open parentheses, this means that it's the function call. Super easy. And then you just like use emit a call, then you do you emit a call, and then you emit the identifier, so run, and that's it. Yeah, so that's it. Kind of easy, and you can also imagine the function call is just like 2 descriptors, the identifier descriptor and the argument list descriptor. I haven't implemented the arg list yet, so it's just a constant 0 all the time, but I can extend it now. I can also see that I need to extend this my function definitions, because you can see here I only have the name of it, the body type, and the descriptor, the var count, how many variables are inside the function, and then also the symbol table for the function. I need to give it another field here, which is the parameter list. The difference between a parameter and a argument is that A, B, C, this is parameters. These are not evaluated yet. These are just like textual ideas. And these A, B, and C actually have a value. So these are like arguments to this print function. So if I put in 1, 5, 4, and 7, this is argument 1 or 0, 1, and 2. And this is parameter 0, 1, and 2. So basically, arguments have value, parameters don't have value until they are run, or until they get assigned a value. Yeah, that's kind of the difference between them. And that's basically it. I have also done the while loops and the the if statements. I believe I have told you about, or maybe shared it with you. I'm not sure, but let's see if I have it. Nope. I have one here. Oh, what's going on? And we're missing something. There we go. So basically a while loop or an if statement is an if statement, and a while loop is basically the same thing. Once you have an if, you basically have a while loop. Or the other way around. Yeah. But you have a guard, and then you have an end of body. Once you read the end of the body, so basically this point, then you want to jump up to this guard. So this is basically what the guard does. It jumps up to the guard, and then we evaluate the expression inside the guard. We can see that it's basically checking if I is less than 10. So we load the variable I, and we push 10. Then we just compare them, and then we say this is a conditional move if this was true. So we do conditional move if it's less, and the queue is just 64 bits. So 64 bits, we want to move 64 bits, and this is a conditional move, so it's move, MOV, and then less, and you can also replace it with a G for greater, or E for equal, or N for not equal, I believe. And then it basically just moves the value of RDX into RCX, and you can see here I have a 1 in RDX and a 0 in RCX, so basically 0 is false, so I just always assume that it's false. And then if it's true, I move in a 1. And then I just basically here check for is the value of RCX, so I push the RCX, is the value of this 1? If it's not, then we jump out of this while loop. And then we have the final print I. That's kind of like how it works. It's the same with if statements. Yeah, that's it. I think that I will implement some of the things here that I have talked about, or not talked about, but that is in my backlog. And once that is done, I will maybe go ahead and either write the next compiler in this language, or I will maybe do more features in assembly, or I will just go ahead and choose a different language to write the next compiler in, maybe C. Currently I'm just practicing how to make a compiler. I find them fun, and I find new ways to do it all the time, and I find dumb ways to do stuff, and yeah, I get progressively better, so that's good. So I can either continue in assembly just for fun, however adding more difficult features will become a very big hassle, because it's difficult to code in assembly. Or I can self-host my language, so I will extend the compiler by using the language that I have written or created. Or I can just use a new programming language to make a new compiler. I don't know yet. I think if I will self-host, I will probably write modules that extend the features of the language, but I will not discard the whole compiler. I will just extend the compiler when self-hosting. So for example, I will probably implement hashing in the language, and I will probably implement some different kinds of data structures, and what else? Also probably peephole optimization, like I talked about, like converting this push pop into a move from Rex to RDI. I could easily do that, but it's more difficult in assembly, easier in a more high level language like this. Or my language is not at high level, but yeah, you get the point. Yeah, so anyways, that is it for this time. I will probably update you once I have implemented all of these features, or maybe before, maybe later, I don't know yet. Maybe once I've only made a decision on what to do. I have no idea. Yeah, but anyways, and you should totally look out this plugin or extension. It's bookmarks, super amazing. Like for this, I have bookmark list, and then I can just like go through all of them. Super easy. Before I used the Control F to like search for stuff, but now I can just like say, okay, it's the while, and then it just jumps there. And it's even fuzzy finding, so I can write S for symbol and then while too, if I have had multiple whiles, for example. For example, I have two different kinds of statements. So if I write C statement, it's symbol check statement kind. If I just write statement, it's symbol statement list. Yeah, so it's super nice, and it's very fast also. I feel like a fast boy. If you do Control P, you can also choose different files, and Control G, you can go to different lines. Very nice. Yeah, whatever. See you next time.